is on the solution of systems of linear equations, Chapter M. When given more than one equation with more than one variable, the problem is referred to as a system of equations. If all the variables are linear, exponent of the variable is 1, that is, and it is not a divisor, then it is a linear system. Otherwise, it is nonlinear. A system of equations with two equations in two variables is called a 2-by-2 system. With two variables and two equations is called a 2-by-2 or 2-by-2 system. Notice that I have written 2-by-2 with a time sign in between, but that it does not mean that 2 is multiplied by 2. This is just general notation as it applies to systems of equations and is read, as I have it in brackets, 2-by-2. For example, 2x minus 3y equals 4, we will refer to that as equation 1, and 5x plus 2y equal to 1 is our second equation. And there you see two linear equations, linear because the exponent of each of the variables is 1 and x is not a divisor, and we have the two variables x and y. For a unique solution to exist, there must be at least as many equations as there are different variables, although this does not always guarantee a unique solution. So even if those conditions are satisfied, a unique solution is not guaranteed. 3 equations in 3 variables is a 3 by 3 system, and so on. So you have 4 by 4 systems, 5 by 5 systems, and so on and on. For example, 2x plus y minus z equals 1. We will call that equation number 1. 4x minus 3y plus 2z equals 4. That's our second equation. X plus y minus 3z is equal to 0, and that's our third equation. For any given system, the solution is the set of values for the variables that satisfy all equations. That is why it is sometimes called a simultaneous system of equations, since all of the solutions to the variables satisfy all the equations simultaneously. So for any given system, the solution, also called roots of the system. For any given system, the solution is the set of values for the variables that satisfy all equations. The largest system we will work on will be a 3 by 3. In the chemical and oil technologies, a system as large as 100 by 100 is not unusual. Computers easily handle systems that large. The first method to solve systems of equation will be the method by elimination. This process involves reducing a system of given size to one of smaller size until a linear equation in one variable is obtained to get the first root. This equation will be a member of that system. That you started with. By backward substitution, the remaining roots are easily found. Consequently, a 3 by 3 system is reduced to a 2 by 2, which in turn is reduced to essentially a 1 by 1, the smallest reduction possible. Or variable. And that is essentially the objective of this process. I will review certain properties of systems of equations now. First of all operations of arithmetic can be applied to the system. In other words, addition, subtraction, multiplication, and division. Any linear equation in the system can be multiplied or divided by any number except 0. Any linear equation may be multiplied or divided by a number except for 0. Let's take 2x minus 3y equals 4, for example. Now, if we multiply both sides by minus 7, and doing it properly on both sides of the equal sign, we have then that the left-hand side is minus 14x plus 21y equals minus 28. And that's as true a statement as the one I wrote in the first place. I can divide both sides by 2, for example. And multiplying both sides by 2, or dividing both sides by 2, will give me 2x divided by 2 is x. Minus 3y divided by 2 is minus 3 over 2y. And dividing 4 by 2 is equal to 2. And this is as true a statement as the first one that I wrote. In any given system, the left side and right side can be added to produce another linear equation, which is different, but still a member of the same system. Let me show this using a slightly different approach. For example, it is easy to see that this statement is true. 3 plus 7 is equal to 10. If I follow that with another true statement, 1 minus 9 is equal to minus 8, I have two equations, if you like. And now, if I add both sides of the equal sign separately, in other words, if I take this side and add vertically, I end up with 3 plus 1 is 4, plus 7 subtract 9 is minus 2. That's the result on the left-hand side. On the right-hand side, adding vertically, I should mention here what I'm doing, that the right-hand side is equal to 2. If you read that statement, you can see that it is also a true statement. In other words, 4 minus 2 is equal to 2. It certainly does not look like any of the other two equations I wrote, but nevertheless, I can add systems to produce a new equation which is also a true statement and is in fact part of the system that I began with. If now I continued with the same two equations and subtracted, notice what happens. I end up with 3 subtract 1 is 2. If I take plus 7 and subtract minus 9, remember that you change the sign of the bottom number mentally and add the result, and the result is 16. If I look on the right-hand side and subtract again, 10 plus 8 is 18. And here is, again, a true statement, but this time I subtracted. If we have an actual system with two equations in two variables, like 2x minus 3y is equal to 4, equation 1, and 5x plus 2y equal to 1, my second equation. I used brackets before, so I will continue to use brackets like that, although that doesn't make that much difference. I can add this system to produce another equation which will look different from the ones I started with, but will still be a true statement and will still belong to the system at hand. If I add, I get 7x, I get minus y, and I get 5. If I subtract, I'll get something different. And I will get here minus 3x minus 5y equal to 3. So each of these results, which look different, belong to the original system. In fact, the solution to the system in black, will produce the same answers for x and y as the solution to the system in red. And that should be expected, since all of these equations belong to the same system and naturally must yield the same roots. I will now show you how using the operations I've just described on systems will lead to its solution. We'll begin with a 2x2 system. The simplest system that we deal with. I'll put a subheading there to remind us that this is what I'm dealing with. 2x minus 5y equals 9. And 3x plus 2y equals 4. Now recall that I explained the main objective in finding the root to the system was to reduce the size of a system to one of simpler size. One essential part of the procedure is to make sure that the variables in x and the variables in y are lined up as I have listed them, followed by an equal sign, and then the constants on the other side. Follow this procedure for all problems dealing with systems of equations. That will at least be a standard that you can follow. You might end up in a question with x's and y's all either on the right-hand side of the equal sign, some of them on the right, some of them on the left, and sort of mixed up that way. So your first observation would be to be sure that they are lined up as I have them. First the x's, then whatever, followed by the y's, followed by an equal sign, and then the constants. Now, notice, as I've explained in my examples dealing with operations that can be applied to systems, that if I add what you're looking at here, I'll end up with 5x minus 3y equals 13. The result is another equation with two unknowns. But remember, I wanted one equation in one unknown. So it essentially requires that I eliminate one of these variables from the system. If I eliminate y, I'll get a single equation in x. Or if I eliminate x from the system, I will end up with a single equation only in y. Well, I'm allowed to multiply or divide both sides of any equation. If I can get the coefficient of x to be the same as the coefficient of this equation, if I subtract, I'll end up 0 in that column. And this is how I establish that objective. If I multiply the top equation by 3, and I'll indicate it like this. 3 multiplied by equation 1 is equal to 6x minus 15y equals 27. And I'll refer to that by a different number since it's a new equation belonging to the system. If I take the second equation and multiply it by 2, I'll end up with the 6x that I was looking for, the plus 4y for this, and the 8 over here, remembering that whatever you multiply on one side of the equal sign, you must also multiply that same number on the right-hand side of the equal sign. And there I have equation number 4. And now, you see, if I subtract I get 0 for that column and end up with minus 19y equal to 19 on the right-hand side. Then y is equal to, divide by minus 19, is equal to minus 1. The next part is quite simple. Since you know what the value of y is, and here you have an equation, 2x minus 5y equals 9, by the substitution of y equal to minus 1 into one of the equations, it won't make any difference whether you use equation 1 or 2. You'll end up with the same value for x. So we write, substitute y equal to minus 1 in equation 1. So we then have 2x minus 5 followed by the value of y equals 9. 2x plus 5 equals 9. 2x equals 4. And finally, x is equal to 2. We have found the roots of the system. It is that x is equal to 2 and y is equal to minus 1. Now, what I want you to do is to write all your solutions in a particular way. Put a bracket followed by x, comma, y equal to, what was x? 2. X is first here, so it'll be first there. Y is next in the brackets here. Y is equal to minus 1, and so minus 1 will go in that position. There will be a purpose for indicating solutions like this shown in another lecture. But for now, simply follow the instructions and write your solutions that way. Let's verify that these are indeed the roots of the original system. Remember that the roots, to be the correct ones, must satisfy both equations. In other words, simultaneously. We begin by writing this proof in the following way, or the verification if you like. Equation 1. Left side is equal to 2x minus 5y, which is equal to 2 brackets 2 for x minus 5 brackets minus 1. This is 4 plus 5, that equals 9, and that is equal to the right-hand side. And I have shown that 2 and minus 1 substituted into the equation makes that statement true. In equation 2, the left side is equal to 3x plus 2y. This is equal to 3 brackets for x plus 2 brackets for y. And I have 2 and minus 1. 3 times 2 is 6. If you subtract 2 from that, the answer is 4. And that is what we have on the right-hand side. 4 equals our S for the right-hand side. The next example will deal with the 3 by 3